There exists a photograph, grainy and poorly circulated even in the post-Soviet era, that shows a titanium-skinned aircraft sitting on a frozen tarmac at the Zhukovsky Flight Test Center. The machine is sleek and predatory, its nose drooped downward like a heron preparing to strike, its wings swept back at a radical angle that suggests violence and speed. Standing beside it, dwarfed by the sheer size of the beast, is a small group of engineers in heavy coats, their breath visible in the cold Moscow air. They are not smiling. They know what this photograph represents, not the future of Soviet aviation, but its most expensive dead end. This is the Sukhoi T-4, known to its designers as Sotka, or the 100, a supersonic strategic bomber that was supposed to carry the Soviet Union into the stratosphere at 3 times the speed of sound, delivering nuclear annihilation to American cities before any interceptor could climb high enough to stop it. It flew only 10 times. It cost more than the entire Soviet space program of the same period. And it was canceled, not because it didn't work, but because by the time it did, the entire philosophy of strategic bombing had shifted beneath its titanium landing gear. To understand the T-4, one must first understand the profound strategic and bureaucratic paranoia that gripped the Soviet military-industrial complex in the early 1960s. This was the era when American propaganda films showed gleaming XB-70 Valkyrie bombers cruising at Mach 3 and 70,000 feet, theoretically untouchable by Soviet interceptors or surface-to-air missiles. The Valkyrie was a 6-engine monster designed to ride its own shockwave across continents, using compression lift to extend its range and speed. It was a statement of technological dominance, and it terrified the Kremlin. Soviet intelligence reports, often exaggerated by analysts desperate to justify their budgets, suggested that the Americans were planning to build hundreds of these machines. The Soviet response had to be equally dramatic, not just an interceptor to shoot down the Valkyrie, but a Soviet equivalent that could penetrate American airspace at similar speeds and altitudes. The problem was that in 1961, when the program was formally initiated, the Soviet Union had no experience building an aircraft capable of sustained flight at Mach 3. They had built the MiG-25, but that was a sprinter, designed for short interception dashes. They had no metallurgy for sustained high-temperature operations, no engines that could breathe efficiently in the thin air of the stratosphere, and no aerodynamic data for compression lift at those speeds. What they did have was political will, unlimited funding, and 2 competing design bureaus willing to destroy each other to win the contract. The competition was between Sukhoi and Tupolev, the 2 titans of Soviet aviation, and it was less a technical evaluation and more a gladiatorial contest played out in the halls of the Central Committee. Tupolev, the older and more politically connected bureau, proposed the Tu-135, a variable geometry bomber that used swing wings to balance takeoff performance with supersonic dash capability. It was a conservative, evolutionary design that minimized risk. Sukhoi, always the aggressive outsider, proposed something far more radical, a fixed-wing delta design made almost entirely of titanium, capable of cruising at Mach 3 for extended periods, with a droop nose for landing visibility and engines integrated into the wing roots for maximum efficiency. It was a design that had never been attempted at that scale. The Tupolev proposal was safer, cheaper, and more likely to succeed. The Sukhoi proposal was faster, more capable, and infinitely more expensive. In a rational procurement environment, Tupolev would have won immediately. But the Soviet system was not rational, it was Darwinian. Both projects were funded simultaneously, each bureau tasked with building a prototype to prove their concept. The winner would get the production contract. The loser would be disbanded. If detailed technical breakdowns of aviation design and strategy interest you, subscribe. I have got more of these coming. The airframe of the T-4 was an engineering marvel and a metallurgical nightmare in equal measure. To survive the thermal loads of sustained Mach 3 flight, where kinetic heating raises the skin temperature to over 300 degrees Celsius, Sukhoi determined that conventional aluminum alloys were inadequate. The solution was titanium, specifically the VT20 alloy, a material that maintained its strength at high temperatures but was notoriously difficult to machine and weld. Titanium work hardens under cutting tools, it catches fire if the welding environment is not perfectly controlled, and it is so reactive with oxygen at high temperatures that entire fabrication facilities had to be built with inert gas atmospheres. The Soviet titanium industry, primarily developed for submarine hull construction, had to be retooled and expanded to supply the Sukhoi project. Approximately 75% of the T-4's structure was titanium, with the remainder being high-temperature steel in the engine bays and some specialized composites in non-load-bearing fairings. The fuselage was a semi-monocoque structure with titanium longerons and frames supporting a stressed titanium skin. The wing was a pure delta planform with a leading-edge sweep of approximately 60 degrees, designed to generate significant compression lift at supersonic speeds. The wing itself was a multi-spar torsion box, immensely strong but also immensely heavy, accounting for nearly 30% of the aircraft's empty weight. The propulsion system was equally groundbreaking. The T-4 was powered by 4 Kolosov RD-36 engines, each producing approximately 16,000 kilograms of thrust in afterburner. These were not off-the-shelf power plants. They were purpose-built turbojets designed specifically for sustained high Mach operations. The engines featured variable intake ramps and shock cones to slow and compress the incoming supersonic airflow, a boundary layer bleed system to prevent compressor stall, and a convergent-divergent exhaust nozzle to efficiently expand the exhaust gases at supersonic speeds. The engines were buried deep in the wing roots, fed by 4 massive rectangular intakes positioned on the underside of the fuselage. This configuration minimized radar cross-section from the frontal aspect and reduced aerodynamic interference, but it created a packaging nightmare. The intake ducts were S-shaped to hide the compressor faces from direct radar illumination, and they incorporated complex variable geometry to optimize airflow across the flight envelope. At Mach 3, these intakes were doing more compression work than the engines themselves. The air entering the compressor face was already slowed to subsonic speeds and pre-compressed by the carefully shaped duct geometry. If the intake flow separated or the shock positioning became unstable, the engine would immediately surge and lose thrust. This instability plagued early test flights and required months of tunnel testing and computational work to resolve. The fuel system was a study in paranoia and redundancy. The T-4 carried approximately 65,000 kilograms of fuel in integral wing tanks and fuselage cells, using a specialized high-temperature kerosene designated T6. This fuel had a higher flash point than standard jet fuel to prevent vapor ignition in the hot tankage, but it also had poorer cold weather characteristics, requiring preheating on the ground in winter operations. The fuel was used as a heat sink for the environmental control system and various avionics, circulated through heat exchangers before being burned. This meant that the fuel temperature would rise during flight, requiring careful management to prevent vapor lock in the fuel lines. The fuel distribution system used a computerized sequencing system to maintain the aircraft's center of gravity as fuel was consumed, automatically transferring fuel between tanks to keep the aircraft balanced. This was critical because the T-4's aerodynamic center shifted significantly with Mach number due to the delta wing's changing lift distribution, and the center of gravity had to move with it to maintain stability. The Avionics suite was the most advanced ever fitted to a Soviet aircraft up to that point, and it showed both the ambition and the limitations of Soviet electronics in the late 1960s. The primary navigation system was an inertial platform the I-12, which used gyroscopes and accelerometers to continuously calculate the aircraft's position without external references. In theory, this system could navigate across continents with an accuracy of a few kilometers, even with all radio navigation aids jammed or destroyed. In practice, the I-12 suffered from drift, particularly during prolonged high-G maneuvers, and required periodic updates from ground-based radio beacons or celestial navigation when available. The radar was the PNA, a powerful terrain-following and mapping radar that allowed low-level penetration in poor weather, but it was also a massive electronic signature that enemy radar warning receivers could detect from hundreds of kilometers away. The defensive avionics included a comprehensive radar warning receiver suite with antennas covering the full azimuth and chaff and flare dispensers for missile defense, though at Mach 3 the primary defense was simply speed and altitude. No missile of the era could catch the T-4 if it was at cruise speed above 20,000 meters. The most distinctive feature of the T-4 and the source of its most complex engineering was the droop nose. Because the fuselage was designed for minimal drag at supersonic speeds, it had a long, pointed nose with a very shallow cockpit canopy. This configuration gave the pilot virtually no forward visibility during takeoff and landing, when the aircraft's nose was pitched up at a steep angle. The solution was a hinged nose section that could be hydraulically lowered by 5 degrees for low-speed operations, giving the pilot a clear view over the nose. This mechanism, seemingly simple, was an engineering challenge of frightening complexity. The nose section had to seal perfectly at supersonic speeds to prevent aerodynamic heating and pressure loads from entering the hinge gaps. The hydraulic actuators had to be powerful enough to move the multi-ton nose section against the aerodynamic loads during transition, yet precise enough to lock it in position with millimeter accuracy. The cockpit windscreen, which was part of the moving nose section, had to maintain optical clarity while being heated to prevent icing, and it had to withstand bird strikes at 400 kilometers per hour during takeoff. The droop nose mechanism on the T-4 was later adapted with significant modifications for use on the Tu-144 supersonic airliner, one of the few tangible legacies of the Sotka program. The flight control system was a hybrid design, blending mechanical linkages with electronic augmentation. The primary flight controls, ailerons, elevators, and rudder were hydraulically actuated but mechanically signaled. The pilot's control inputs moved cables and rods that positioned hydraulic valves, which in turn drove the actuators. However, overlaid on this mechanical system was the AU-37 automatic flight control system, an analog computer that provided stability augmentation and autopilot functions. The delta wing planform, while efficient at supersonic speeds, was inherently unstable at subsonic speeds, particularly in pitch. Without constant pilot attention, the aircraft would develop a pilot-induced oscillation in the landing pattern that could quickly diverge into a dangerous porpoising motion. The AU-37 damped these oscillations by continuously monitoring accelerometers and gyroscopes and making small, rapid control inputs that the pilot could not match manually. The system was always on. Turning it off rendered the aircraft nearly unflyable at low speeds. This reliance on electronic augmentation was a preview of the fly-by-wire systems that would become standard decades later. But in the late 1960s, it was a source of deep anxiety. Pilots did not trust the computer, and the computer frequently malfunctioned. The cockpit itself was a cramped, purely functional space dominated by analog instruments and warning lights. The pilot and navigator sat in tandem, each in a separate pressure capsule designed to eject as a unit in an emergency. These capsules, rather than traditional ejection seats, were necessary because at Mach 3, the dynamic pressure outside the aircraft was so high that a conventional seat ejection would result in the pilot being instantly torn apart by the airstream. The capsule system, designated the SPK system, was designed to separate from the aircraft, decelerate using a drogue chute, and then deploy a main parachute to bring the entire capsule to the ground. The crew would remain inside the sealed capsule throughout the descent and landing, protected from the elements. In theory, this system could save the crew at any speed and altitude. In practice, it was never tested in an actual emergency during the T-4 program, so its reliability remained a comforting myth. Knowing what you now know about its design and engineering challenges, do you think the resources invested in the T-4 program were justified given the strategic shift toward ICBMs? Share your thoughts below. The T-4's maiden flight took place on August 22, 1972, flown by test pilot Vladimir Ilyushin, son of the famous aircraft designer Sergei Ilyushin. The flight was a cautious 35-minute sortie, with the landing gear extended throughout to reduce risk, reaching a maximum speed of only 400 kilometers per hour and an altitude of 1,200 meters. It was a test of basic airworthiness, and by all accounts, it went smoothly. Ilyushin reported that the aircraft was stable, responsive, and free of any alarming vibrations or control anomalies. But this first flight, while a propaganda victory for Sukhoi, revealed nothing about the aircraft's high-speed performance. Over the next 10 flights, conducted over a period of approximately 2 years, the test program gradually expanded the envelope. Maximum speed eventually reached Mach 1.36, and altitude reached 17,000 meters. These were impressive numbers for a first-generation prototype, but they were nowhere near the design goals of Mach 3 and 24,000 meters. The problem was not the airframe or the engines. Both were performing as predicted. The problem was the political environment. By 1973, the strategic calculus that had justified the T-4 program had completely collapsed. The American XB-70 program had been canceled in 1969 after building only 2 prototypes, one of which had been destroyed in a mid-air collision. The Americans had concluded that supersonic bombers, no matter how fast, were obsolete in an era of improving surface-to-air missiles and space-based reconnaissance. The future of strategic deterrence was not in manned bombers, but in intercontinental ballistic missiles and submarine-launched ballistic missiles, which were faster, cheaper, and invulnerable to interception. The Soviet leadership, always attentive to American strategic developments, began to question the wisdom of investing billions of rubles in a manned bomber program. The Tupolev Tu-160, a subsonic strategic bomber with intercontinental range, was already in service and performing adequately. The idea of replacing it with a Mach 3 bomber that cost 10 times as much and carried a similar payload seemed increasingly irrational. Furthermore, the Tupolev Bureau's competing Tu-135 program was maturing, and while it was not as fast as the T-4, it was significantly cheaper and more versatile, capable of carrying both nuclear and conventional payloads. The political winds were shifting toward Tupolev, and Sukhoi could feel the ground eroding beneath them. The operational requirements for the T-4 were also becoming clearer, and they were troubling. The aircraft required a runway of at least 3,000 meters, which limited it to major strategic airfields that would be priority targets in any conflict. Its takeoff weight was so high that the landing gear exerted enormous pressure on the tarmac, requiring specially reinforced runways that did not exist at most Soviet air bases. The maintenance requirements were staggering. The titanium airframe required specialized tools and training, and the engines needed to be inspected and overhauled after only 50 hours of operation due to the extreme thermal and mechanical stresses of high Mach flight. The turnaround time between sorties was measured in days, not hours. From a logistical standpoint, the T-4 was a nightmare, requiring a support infrastructure that the Soviet Air Force simply did not have and could not afford to build. The comparison with its contemporaries is instructive. The American XB-70 Valkyrie, which had inspired the T-4 program, was a larger aircraft with a maximum speed of Mach 3.1 and a combat radius of over 6,000 kilometers. But it required a crew of 4, was even more maintenance-intensive than the T-4, and was so expensive that the U.S. Air Force canceled it in favor of the B-1, which was subsonic but more practical. The British TSR-2, another supersonic bomber program of the same era, was canceled before it flew operationally, a victim of budget overruns and strategic reassessment. The French Mirage 4, a smaller tactical bomber, achieved Mach 2 but had a limited payload and range. What all these programs had in common was that they represented the end of an era, the belief that speed and altitude alone could defeat air defenses. The reality was that improving radar, surface-to-air missiles like the American Nike Hercules and Soviet S-75, and eventually airborne early warning systems made high-altitude penetration suicidal. The future belonged to low-altitude penetration, terrain masking, and eventually stealth technology. The T-4 was a technical masterpiece designed to fight a war that would never be fought. The final flight of the T-4 prototype occurred in January 1974, a routine test flight that ended without incident. Shortly afterward, the program was officially terminated. The decision was announced with characteristic Soviet brevity. No public statement, no detailed justification, simply an internal directive that funding would cease and the engineering teams would be reassigned. The prototype was placed in storage, eventually ending up at the Monino Air Force Museum where it sits today, slowly corroding under the open sky, a monument to ambition and miscalculation. Estimates of the total program cost vary widely, but Western analysts suggest it consumed somewhere between 800 million and 1.2 billion rubles, an astronomical sum in 1970s Soviet currency. To put that in perspective, it was roughly equivalent to the cost of developing the Soyuz spacecraft program over the same period. The engineers who worked on the T-4 speak of it with a mixture of pride and bitterness. They had solved problems that no one had solved before: titanium fabrication at scale, supersonic intake design, thermal management for sustained high-speed flight. They had built an aircraft that, in its limited test program, had demonstrated performance that matched or exceeded Western equivalents. And yet the program had been canceled, not because of technical failure, but because the mission had evaporated. There is a particular frustration that comes from succeeding brilliantly at a task that turns out to be irrelevant. The T-4 did leave some tangible legacies. The titanium welding and fabrication techniques developed for the program were later used in the construction of Soviet submarines and the Tu-160 supersonic bomber. The engine technology from the RD-36 was adapted and scaled for use in other programs. The droop nose mechanism was refined and installed on the Tu-144 airliner. The experience of integrating complex avionics and flight control systems informed the development of later Soviet fighters like the Su-27. But these were secondary benefits, consolation prizes for a program that had consumed vast resources and delivered no operational capability. There is also a broader lesson about strategic aviation programs and the dangers of designing for a threat that may not materialize. The T-4 was conceived in an era when American strategic bombers seemed like an existential threat, and speed was seen as the ultimate defense penetration capability. By the time the aircraft was flying, the threat had shifted to missiles, and speed was irrelevant. The program illustrates the difficulty of long-term procurement planning in a rapidly evolving strategic environment. Aircraft take a decade to develop. Strategic realities can change in a year. The Soviets were not unique in this failure. The Americans canceled the B-70, the British canceled the TSR-2, the Canadians canceled the Avro Arrow. All were victims of the same phenomenon, the bomber gap that never was, and the missile age that arrived faster than anyone predicted. From a technical standpoint, the T-4 was arguably more advanced than the XB-70 in certain respects. The Soviet aircraft had better thrust-to-weight ratio, simpler and more robust systems, and a smaller logistical footprint. But it was also less ambitious in range and payload. The XB-70 was designed to carry 10 tons of weapons over intercontinental distances. The T-4 was designed for a lighter payload over shorter ranges, reflecting the Soviet doctrine of forward-deployed strike assets rather than continental reach. Whether this made the T-4 a better or worse design is ultimately a question of doctrine rather than engineering. The fate of the Sukhoi Design Bureau in the aftermath of the cancellation is worth noting. The Bureau did not disband, but it was politically weakened. Tupolev's Tu-160 and Tu-22M bombers became the backbone of Soviet strategic and theater strike forces. Sukhoi pivoted to fighter design, eventually producing the Su-27, one of the most successful fighter aircraft ever built. But the institutional memory of the T-4 remained, a reminder that even the most technically brilliant program can be strategically obsolete. Sukhoi engineers who worked on the T-4 have said in interviews that the experience made them more skeptical of paper requirements and more focused on practical operational utility. It was an expensive lesson, but it was learned. For aviation enthusiasts and historians, the T-4 occupies a unique position. It is not a combat legend like the MiG-21 or Su-27. It is not a disaster like the Yak-38. It is something more ambiguous, a successful prototype of an unnecessary aircraft. It flew, it worked, and it was canceled. There is a melancholy quality to its story, a sense of wasted potential. One can walk around the prototype at Monino and see the craftsmanship, the attention to detail, the sheer audacity of the design. And one can also see the rust, the missing panels, the weeds growing around the landing gear, the physical decay that mirrors its historical obscurity. If the Soviet Union had continued to fund the program, could the T-4 have become operationally viable? The technical obstacles were solvable, engine reliability could be improved, maintenance procedures streamlined, operational costs reduced through economies of scale. But the strategic question remained unanswered. What would it do that an ICBM could not do better? Manned bombers have certain advantages. They can be recalled, they can loiter, they can respond to changing intelligence. But at Mach 3 and 20,000 meters, the T-4 had almost no loiter capability. Its fuel consumption at cruise was so high that it had little endurance. It was a strategic sprint weapon, not a flexible platform. And in a strategic environment increasingly dominated by submarines and missiles, that niche was vanishingly narrow. The comparison with later supersonic bombers is also revealing. The American B-1, which entered service in the 1980s, was a variable geometry design optimized for low-altitude penetration at high subsonic speeds, with a secondary high-altitude dash capability. It was practical, versatile, and expensive, but sustainable. The Soviet Tu-160, which filled a similar role, was a swing-wing bomber that never achieved the T-4's speed, but was operationally flexible and logistically manageable. Both of these aircraft represented a retreat from the pure supersonic bomber concept, an acknowledgement that Mach 3 was not the answer. The T-4, frozen in time as a Mach 3 design, became an evolutionary dead end. For those who study Cold War aviation, the T-4 is a case study in the gap between technical capability and strategic utility. The Soviets could build the aircraft, they proved that, but they could not justify operating it. It is a distinction that is easy to overlook when examining specifications and performance numbers. But it is the distinction that determines whether a prototype becomes a legend or a museum piece. If you found this analysis useful, a like helps more people discover these deep dives. Thanks for watching.